Hello, Ketna. Can you hear me?
Yes, sir.
Okay. So, in the last class, what we discussed,
Magnetic momentum due to rotating bodies.
okay, makes sense. So, look, in the yesterday's chapter, okay, from the today's, we are going to start with magnetic induction. Yes, electromagnetic induction, we are going to start. So, from here, itself, we are going to start. So, look, this chapter is quite important, so you need to give you time over here. So, with the chapter, electromagnetic induction. EMI, the electromagnetic induction. So we are start with the topic magnetic flux. Why? Because in this chapter we are going to use it many times. This is very useful in this chapter. So just once I'm going to describe it because we have already studied this, right? If you have any doubt in the magnetic flux, then let me know. I'll take it once. So what is magnetic flux? Is a physical quantity which represents the number of magnetic field, magnetic lines of force, number of magnetic lines of force passing through participants, such passing through surface. So how you are going to define the things? Assume that I have some surface. Yes. You know that area vector is always perpendicular. So assume this is going to be area vector. Yeah. Now we have to say that there is a magnetic field which is going in this direction. So look here now, what we are talking about is the angle between this this area vector and this magnetic field. Okay? Look, this area vector always don't have to take perpendicular to the surface. Okay? This is the surface, you have to take always perpendicular. So what is the magnetic flux over here? So this flux comes out as B dot S. This is what you have put in or in further. B is for forward. This is going to apply in a bigger picture also, smaller picture also. So if I just talk about the unit, we have already studied this one, okay? That is Tesla for this one, and surface area, that is meter square. In another word, there is one more specific unit for this that is called Weber. Clear? That is called Weber. Also, magnetic fields unit can be written as Weber per meter square. How? Because you can see this Tesla meter square is equals to Weber, so Tesla can be written as Weber divided by meter square. So that's how the both of things. Sometimes you will see magnetic field is written as Weber per meter square. So here in this case, now we have taken magnetic field to be constant. What if the magnetic field is inconsistent? Assume that if B is not uniform, Assume that this kind of figure magnetic field is used. You can see this is not constant, right? How? Because the closeness between magnetic field describes strength. So I can simply say here it is more closer, strength is more here, so the strength is different. Right? What if I go and say that this kind of surface is there? We have this kind of surface to talk about. So I can simply say that at this particular point, at this point, magnetic field is tangent, right? This is the tangent. Okay, makes sense. Yes. Let's make it upside. So if I if I just take it, talk about this point here, so you can see this magnetic field here is at this point magnetic field is tangential. Right? This is tangential direction. B. Okay. Whatever area vector is the same. So you need to, in that case, what you need to do, simply go and say, I am going to take a small area vector that is ds. Okay, magnetic field is this. So you can simply say the flux d flux comes out as d some function. Okay, we don't know what is that function. Dot ds. You need to do this and then just integrate it depending on upon what kind of function you are using. Okay? So this is what you need to do. So now this is starting of electromagnetic induction and I have started with magnetic flux. So if you have any doubt in magnetic flux, please let me know.
No doubt.
No. So let's talk about the main thing. Okay? Due to which this chapter is, we are talking about this chapter. That is Faraday's law. Okay? If you don't know this law, it means you don't know EMF. Just one statement and this complete chapter is all about. Okay. So Kirtana, before this thing, what we used to do, if you want to create some potential difference, what you need to do? You needed to create some chemical energy, right? For example, if in chemistry you have studied galvanic cell. In galvanic cell, right? We used to create potential. How potential was created? Because the chemical reaction was happening. Right? From this plate, the electrons were moving downside. It was becoming positive. This electron was depositing here, so it will become negative. So you can say the positive here, negative. This kind of voltage we are creating, and you can connect this to a circuit, and this is how you are going to get. But what Faraday's law says that makes everything different. Okay? So let's talk about one thing. A story. Let's a small thing. Assume you are having a loop. Okay, and there's some magnetic field in this loop. What kind of? Okay, how you can do this? It's very simple. If you have some loop, keep a north pole of a magnet towards it because from north pole magnetic field goes like this. So if you keep it very close, it will look like this, exactly like this. Okay. If you see from here, so you will see magnetic field going inside. So what you need to do is conduct loop. Now, Kate, now you have conducting loop. What Faraday's law says that there is definitely he had an observation that if you have some loop, okay, this is not for reserve. Earlier, this was the condition. So, if this was the condition, what we did when you took it more closer, assume this reaches here. So, how magnetic field is there? Magnetic field is like this. So, the thing is, during this thing, when you take it from here to here, we saw some current in this. Okay, what we saw? We saw some current in this. Wait, what I'm trying to say? I'm saying there's a current. Are you getting my point? What we are doing right now. Initially, when we started that you had a charge on rest. I moved charge, I got current. Okay, I had some current. And then we said if there's a charge moving, you will be having magnetic field due to that. Okay. Because charge is also moving inside a wire that is acting as a current, making means current will produce magnetic field around it, right? At some point, makes sense. Now, but what I'm trying to say, you had some magnetic field here. Okay, you had the loop, you had some magnetic field, but not the magnetic field. If magnetic field is only providing current, there should be some current, but it is not there. When did you notice the current? When you made some changes, when you put this north pole more closer to it. Mean to say, when you take it like this, you saw some current in this. Makes sense. So what is the name of that current we have doing? That is called induced current. Why induced current? Because you made some changes and you induced a new current. Okay, understood my point. So from here we are talking about induction. Yeah.
Yes, sir.
So look, before coming to a final paradox, this is some experiments what he did. Okay. So what was his main experiment? His experiment was like there was circular loop. He had a magnet over here. He did one thing. He just kept it more close outside. So what he did, when you keep the magnet as it is, what I'm trying to say, when you keep magnet as it is, there is no current. When you take inside, magnet will be in one direction, but when you take it outside, the magnet will be in opposite direction. Understood my point? So this moment of magnet is providing you current. Okay, but is it really to saying that it is due to the magnet? Is it due to the magnetic field? Understood? Why magnetic field is more generous term rather than magnet? Because you can produce magnetic field without a magnet. How? You know, current carrying wire also generates magnetic field. It means to say, if by somehow I'm having current carrying wire, okay, or you can simply say I have a solenoid, right? In solenoid also magnetic field is there, right? Do I have magnet? No, there is a magnetic field over it. Understood. So that's why I'm saying it's better to use a generous term that is magnetic field instead of using a magnet. Magnet instead of using a magnet. Mm, okay, so this is one thing. So what was the one observation? Uh, yeah, when magnetic field was changing, there was some current over here. Okay. Now, what you can have is there was one more experiment. In that experiment, assume this is an axis of a circular loop. This kind of circular loop is there. It is placed inside a magnet. What kind of magnetic field? Like this. Now, what you did here, instead of changing, look, earlier what you are doing, you are taking this magnet inside, you are taking this magnet outside. But here, what you are doing, instead of doing this, you are just rotating this. Okay, how this is happening? Let's see. Assume when the magnet was in this condition, all the magnetic field was passing from this, right? And because it is perpendicular, but when you rotate it a little bit, sometime it came out like this. Nothing is passing through this, right? So can I say the magnetic field is same amount of flux link, amount of magnetic field going inside is varying, right? So it means if varying or varying magnetic flux is there present, then current can be induced. Current can be induced. Okay. Look, you need varying magnetic flux. Although this all started by saying magnetic field, but yes, uh, how does magnetic field is really worth it? Because assume loop is here, magnetic is here, it always has a constant magnetic field, right? How we are saying this magnetic field is useful for this? When this is linked, it means amount of magnetic field linked. If the amount of linked magnetic field is changing, it means uh, amount of linked magnetic field is changing can produce or can induce electric current. Clear to it now this time?
Yes.
Understood why this happens? Because look, in this case, the loop was same. What you are doing, you are just pushing magnet in and out. It means you are making the link of magnet, like you are just giving it more magnetic field and taking and giving less magnetic field. Okay, that makes changes. In the second case, you kept magnetic field constant, but you started rotating the loop. When loop was rotating, you could see, right? Sometimes the magnetic loop, if I say this magnetic field is in this, okay. Once the loop is like this, complete like this. Okay, this is the center and this is the plane. So in that case, you can see it is going perpendicular. But when it gets rotated by little bit margin, it came into this position. Maybe it looks the same, but yes, just think of it once, that it's now its area vector is in this direction, there is some angle. In this case, area vector is like this also, and magnetic field was like this also. Okay. Here the angle, you can, okay, assume the magnetic field direction is this. Yeah, here you can say the angle is theta, here angle is 0. So when you started rotating, this angle theta varies, right? That gives you the flux change, how much the link amount is there, because the flux is itself the measurement of how much magnetic field lines are linked with your magnetic loop. Okay, that loop can be circular and it can in a forest finish. So what are the two main things what he said? Observation is a law. Fine. First law says that first, in a in a conducting loop, conducting loop. Okay, if it is non-conducting, then there is no point of it. In a conducting loop, if magnetic flux in changing, flux is changing, then EMF and current will be generated. Okay, then current are induced. Now you can say, sir, you are just earlier you told about current, but how this EMF thing? It's very evident that if there is presence of current, it must be due to some potential difference. Okay, you need a potential difference to generate current. What is the current? Current is nothing but motion of electrons from one position to another position. That is only going to happen if this is a higher potential, this is a lower potential. They can only move from lower to higher. It means if the current in loop is in this direction, it means there must be some point where if you go to this direction, you will reach to some lower potential. Maybe this is higher, so electrons are trying to move from here to here, this position. This kind of thing can happen. Current, then EMF and current are induced. Okay, so this is the thing. Also, what is the measurement? The induced EMF and okay, let's do not about. We know the measure of this. Induced EMF is always equals to rate of change of magnetic flux. Okay, now just think of it once. Let's go through both of the statements. Okay? First statement says that if you have a loop or something, okay, if you have a varying magnetic field, it will generate EMF and that would generate the current as well. Okay. Second statement says that the induced EMF, what is the measurement of that? That is going to be equal to rate of change of flux. Look, it's not equal to flux, it is rate of change of flux. It means EMF is going to be equal to magnitude. We are, because we don't know the direction now, so I'm just keeping the magnitude. That is going to be equal to rate of change. Means the change of flux is divided by change of time. Can be written further as d phi by dt. Understood? This is what the EMF coming out. Is that clear? Further, you can rewrite this thing as E is equals to change in flux divided by time. Clear? That's how you need to remember it. So if you see this is just the change, it means if I say this is your flux, sorry, this is your flux graph, this is your time graph. So what you can say that assume your flux graph goes like this. It means to say your flux changes from here to here from time t1 to time t2. In this case, if I ask you what is the change in flux, you can simply say that the change in flux is nothing but because we are not adding or something. We are saying just the different values. So from here to here, what is the average change? That is this from this point to this point. It's like you can think in another way. You can make it like this. Okay? So you can see you have started from here, you are ending here. It means this right? This change. This is the change. So you can see the slope will give you the magnetic. It's clear. Here the slope is going to give you the magnetic flux. Understood? If you wanted to go for instant, this is average. If you wanted to go for instantaneous, go for some time t. Need to save this one. Put it like this. So this E will come out as d pi by d. Okay. Clear it now? So this is a small description of Faraday's law. It's not completed yet, but we'll discuss a little bit more. Then we'll come to the Faraday's law. So before going to Faraday's law further, we'll talk about Lenz's law first, and then we'll move back to the Faraday's law. Okay? Lenz's law, because sometimes you will feel that Faraday's law seems to be incomplete when we don't know about Lenz's law. Okay, so look here now. Can you repeat what Faraday's law is all about before going to Lenz's law?
The EMF, induced EMF is equal to rate of change of magnetic flux. And in
Yes.
conducting loop, when magnetic flux is changing, EMF is induced.
Okay, makes sense. Look, so similarly, before that, what Lenz's law says that Lenz's law says that what he says nothing actually. Assume there's a loop, there's a current. Okay? No, there's a loop and there's a magnetic field. What he says that if if actually now by seeing this you will actually understand it little bit how. Look, what Faraday's law says that he says that if this is a loop, okay, if there's a magnetic field, it is increasing or decreasing, there will be current, right? Let's see what Lenz's law says that. Lenz's law says that uh, he says that whatever the changes are there, whatever the changes are happening opposite. What does this mean? Opposite. Okay, this is what he said. He said in a small term. Okay? What does this mean? Uh, okay, let's think in another way. The changes in flux is opposed by induced EMF or current. What does this mean, Ketna? Let's see. Look, I am saying that initially, look, Ketna, if I say initially there is no magnetic field in this, okay? Now I am saying I have a bar magnet. If I go right now, bar magnet is looking like this. I am saying let's do one thing. Let's keep it together. The moment I keep it near for a very second, the moment this flux link, can I say you have made some changes, right? Can I say that? Earlier the magnetic field was zero. Now you took magnetic field near to it, and this amount of flux is linked. So can you see? Can I say that this has been changed? We did till now.
Yes.
Yes, right? Okay, but what Lenz's law says that he says uh, this EMF, this magnet EMF and the current induced opposes this. How it is going to oppose it? Look, you wanted to oppose the change. It means if this is a loop, there's a magnetic field getting linked in this way. You wanted to oppose it. How you are going to oppose it? Can I say if some magnetic field is coming out this way, you wanted to oppose it. It means you need to create some magnetic field like this way, which can cancel it out. Maybe if it is B, it should be B also. Change, cancel out. Can I say this? This is what you wanted.
Yes.
Is it what you need? Yes, you did. But how we are going to do this? Look, you got this using magnetic field. But how you are going to create a magnetic field in this direction? So this what happens over here is EMF gets induced. EMF gets induced basically just think of current now. The current will be induced in such a direction such that this change gets opposed. Now Ketma just tell me, I am saying I wanted to oppose this current, this magnetic field. It means I need to make magnetic field like this, right? My current should flow such that I get this kind of magnetic field. Can I say this? So what in which direction I need to get magnetic field? Can I say if my current flows in this direction, my magnetic field is going to go in this way, and that is going to oppose it. Is it? This happens only when changed. Doesn't mean that if you go and keep magnet like this, the current will always be flowing. No, the current will flow only for an instant when you put it like this. Okay, just for that instant. The moment you stop it, the current will also stop because it is all about the change, not for the permanent thing. Okay, this is not a permanent current you are going to do. It is a change. Clear?
Yes, sir.
Understood, Kitna? What you understood about the Lenz's law? Lenz's law says that changes in flux gets opposed by the current. Okay. Okay. Or in other words, it's better to not write in this way. Yeah. Induced EMF, okay, induced EMF or current always oppose the cause of their existence. Look, why we are writing this? To get a perfect direction of both. What does this mean? Look, I said, Kate, now this is a loop. When you provided this magnetic field, there's an induced EMF, right? But we don't know what is the direction. So I said, it is going to oppose your existence. Who is the existence? What is the cause of their existence? This magnetic field. It means this increase in magnetic field is the reason. It means this EMF will be generated in such a way that magnetic field gets decreased, right? It doesn't mean that the magnetic field is going to get decreased for permanent way. No. Assume initial magnetic field was zero, you link some magnetic field 10 Tesla. So for that moment, when this magnetic field changes from 0 to 10, there will be a current in such a way, maybe downside direction, so that magnetic field generates in this direction due to this loop. Because in this loop, if current is there, magnetic field is going to generate, right? So that's how you are going to get a magnetic field in this way. That is going to be 10 Tesla. Because after this 10 Tesla, this side it is constant. It means it is not going to do anymore. Okay, just for that instant. Is that clear? Look, it means it is going to oppose the cause of existence. What does this mean? If change uh, in magnetic field is positive, what is this? It means increase. It means this induced current will try to decrease it. Will try to decrease it. If change magnetic flux is positive, negative, it will try to increase it. It will try to increase it. Now let's go back to the same position. Now say that you said you kept magnetic from 0 to some value Tesla. Okay, you maintained it. Now you can see the magnetic flux is linked like this. But what if it was due to this, right? What if I took this magnet outside. If I go and keep it more outside, what will happen? My flux in this is going to get changed. My magnetic field here is going to change from 10 to 0. Okay. The change in flux is going to induce some magnetic field and EMF. Okay. But EMF is induced in such a way that change such a okay. This EMF is going to induce in a way to oppose your change in flux, right? What does this mean? Flux was like this, it is going towards zero. It means earlier it was this, right? It is going to decrease. It means magnetic field is going to generate, current is going to generate such a way the direction of magnetic field due to that current should be in this direction to support it, right? Earlier it was 10 Tesla, we are making it 0 degree. So on this instant, when it is going from 10 to 0, it will maintain itself 10. How? It will generate a current in up direction which will maintain current in magnetic field in this direction. Kirtana, is this part clear? This legislator.
Yes, sir.
Okay. So in one word, if I have to write, let's see, I just thinking about one word. Okay, this is a very key importance of Lenz's law and what is that? Faraday's law. The rest of the things which we are going to in this chapter is not that important. Just some formulas we are going to discuss. So if you are good in these points, then it will be helpful for you also. So look, if if in this loop magnetic field is going to increase, can I say flux is going to increase? Yes. What does this mean? Flux is increasing, so induced EMF will be in such a way that E induced or I induced, it will, what it is going to do? It will make your flux down. Clear? It will try to maintain flux on in decreased position because it is trying to increase. If something is increasing and you don't want to see any changes, you will decrease that, right? So this is what it is happening. If magnetic field is decreasing, flux is decreasing, this induced EMF and induced current will try to increase it. Yeah, this is what going to happen. Okay, he states that induced EMF or current will always oppose the change in linked magnetic field. Okay, linked magnetic field, or it's better to call when we talk about linked magnetic field, it means we are calling about magnetic flux. Okay, this is what I'm talking about. Right. Yeah, so I don't think any doubt is there till this point, right?
No, that's
Not right. Okay, just a second. Okay, so let's take an illustration over here. Yes. Okay, Kate, now so look, assume this is a magnetic field. Right now, this is some source of magnetic field, and this is providing inside magnetic field. This is a circular loop. Now, what is happening, Kate? Now, because you can see the magnetic field is inside. What is happening? This magnetic field is increasing, right? Loop is constant. If magnetic field is increasing, can I see the flux is also increasing? Yes. Can you tell me, Kate, now? what will happen to oppose this change? The value of magnetic field is increasing. In if you wanted to see from side view, it will be looking like this. Magnetic field value is going to increase. Earlier it was 0, 10, then 20, and so on. Something is happening. So, what do you think, Etna? What will happen in this case? From this particular loop, magnetic field is trying to increase, which is keeping the change in this flux.
Flux should be decreased.
Flux should be decreased, but how it is going to decrease? Should I need to provide? Do I need to? Okay, what I need to do? Because here from here, flux is increasing. Do I need to put another magnet for other side? What's going to happen over here? Yeah, great. Now what will happen? Great. Now,
Then
okay. You know that when changes the magnetic field is increasing, it means to say magnetic flux is increasing. Is it directly saying that change in flux, increasing or decreasing mean to a change, right? Can I say we are increasing or we are basically changing the flux,
yes,
right? Okay. What happens in this case when magnetic flux changes? It means there will be some current induced, right? Can you can you tell me the direction of magnetic field in this case? No, sorry. Can you tell me the direction of current induced current basically? From my point of view, you need to tell, like because you are seeing some in some screen, so you have to tell by saying clockwise, anti-clockwise. In that way, just tell me what is going to be the direction of magnetic field, or what is going to be the direction of current and why.
anti-clockwise.
Anti-clockwise, okay, but why anti-clockwise? Why not clockwise?
Because for the magnetic field of this, the current is clockwise. And to decrease it, it should go in opposite direction.
Okay, makes sense. Because look, if magnetic field, assume I'm saying, let's say current is this way. Due to this change, the current induced this way. Okay, let's see. If current is due to this way, use right hand thumb rule. Put your thumb this side, palm will be this side. It means palm will be shown towards you. It means this is like this. Magnetic field is increasing this way. Current is going this way. It means this due to this current magnetic field is okay. Makes sense. It is opposing it. Opposing it means to say yes, this is correct direction. If you do in reverse, if you make it like this, it is this. It means you are supporting the change, but you need to oppose the change. It means this is going to be the direction. Understood? That's how Kirtana we have to decide what is going to be the direction of induced current in further whenever we are going to solve a problem. Okay, clear? Okay. Also, because this is changing the current, you can simply say it is acting like there's a small battery. How the battery should be there? Because I told you, if current is going this way, it must be going from higher potential. Assume this is a higher potential. There must be some lower potential. Assume this is a lower. So it is going in this. So this is an EMF. What is the value of this EMF? It can be at any point. Okay, you can make it any point. What is the value? I already told you EMF will be nothing but change in flux, rate of change of flux. So this is going to be the value. This is clear.
Yes, sir.
Okay. Right now we are actually keeping it this thing. Okay? We'll it's later on we are going to put the exact value and all. So let's see, Krishna. I have a one problem. Assume that example you are given infinite current. Okay? infinite rod, and current is I. There's a loop. Okay, there's a loop having some area. In this current is increasing. How this current is increasing? By the time by the time this current I is increasing. Okay. So can you tell me, kids, now what kind of induced current you are going to see in this loop? Can you tell me the direction of induced magnetic field here? What is the direction of the induced magnetic field in this loop? Yeah, kids, now let me know first.
Anti-clockwise.
Yeah, kid, now what you just said?
Anti-clockwise.
Anti-clockwise. Why anti-clockwise? What's the main reason behind having an anti-clockwise current over here?
Due to the wire, the current in the loop is clockwise, so it is anti-clockwise induced.
The current is clockwise. I didn't understand that part. Look, why we need anti-clockwise current in this loop?
Due to the wire, the current in the loop is clockwise, sir, but the induced is opposite, so it is anti-clockwise.
Wait, due to this wire, how the current is clockwise in this loop? We are not even talking about current. We are just talking about yeah. Why, like, how this current is contributing to the induced current here? What was the main reason for this? It's not, look, the main reason is magnetic field, right? If there's a current, there's a magnetic field. Due to this current, there's a magnetic field at this point, right? In this region. Because this current is increasing by the time, right? By the time it is increasing, this magnetic field is increasing. Increasing magnetic field, there will be current. And we have already said for this inside going magnetic field, this anti-clockwise, okay? This is one thing, but if one more thing, look, current is now like this, right? This current will be make magnetic field this induced magnetic field. You can call this as BI, sorry, induced. You can call this as B. Wait. Here, this is induced magnetic field, B induced, and this is BI. Okay? This they are going to get cancelled out each other. Understood? Also, you can say, sir, this is a magnetic field, right? There's a magnetic field inside. There's a current also. So what will happen? There's a force also, right? Understood? There will be a force too also. Okay. So look, I'll actually make it a little bit bigger so that you can understand it in better way. Now just think this paradox in a little. Look, this is a loop, right? We said due to this current there is a induced EMF. Okay, there's an induced EMF. You know, Krishna, if current is there, right? There's a force. What is that force? Force is nothing but current L cross B. What is the direction of length? You can say, sir, this is L and B is inside. Due to this I, the magnetic field is always inside. So what is the force on this? You can simply say, sir, force is downside. Okay. What about this? Force is this side. What about this? This wire force is upside. What about this? Force is this side, right? Is it the force? Yes. This is the direction of force you are going to be clear. But there's a thing. Magnetic field at this point is same. Magnetic field this point and this point is same. Magnetic field this point is same. It means whatever the magnetic field getting here is same. It means the net magnetic field at this, net force on this, and this is also same, right? This gets cancelled out. This gets cancelled out. This F got cancelled. What about this F towards right, F towards left? Here the magnetic field is greater than this always because distance is changed, right? All that is increasing. So maybe earlier it is 20, it is 40, it will be then 40, then 60. Something it is going to increase or decrease. Okay, at the same time. I can simply say F times of R, FR is greater than FR minus FR is greater than FL. What does this mean? This means there will be small force on it. Understood? There will be small force. Due to this, this wire will shrink. Look, Krishna, what is happening here. Earlier, the wire was like this. Because of the force, the wire shrink. Due to this shrink in wire, whatever the extra flux went, you increase the magnetic field, right? But area decrease. What is the flux? That is B dot S. You increased B, but S decreased. This makes flux constant. Understood? That's how things happens. Okay? Does it make sense?
Yes, sir.
So you can see the flux changes created a magnetic field. What is that? Yeah, the flux change created an electric field. Electric field induced in a such a way that it opposes the change. How is it oppose the change? It simply make a condition where your flux can shrink a little bit from all the side so that this happens. Is that clear? Yes, it might be clear. Okay. So yes, Kirtna. Yeah, Kirtna, that's all for the today's session. We'll do some problem in the next class also. Clear?
Yes, sir.
Yeah, Kirtna, then that's all for the today's session. Goodbye. I'll be sharing these 3 to 4 whatever the skills are.